is, sorry, Vance Roux, I think. Is that correct pronunciation?
You are one of the few people in the world who pronounce it correctly. Yes.
Oh, wow. Thank you. Vance Roux has a master's degree in mechanical engineering, and he is together with colleagues, one of the first to and the company of Planet Research were the first in the world to successfully simulate the icy regolith components, and also to perform the first measured extraction of these components. That sounds very exciting, and we will now hear about progressive stages of establishing an enduring and thriving human presence on the moon. The floor, the air, and the ether is yours, Vance.
That's a lot to have control of. Thank you very much, Nicholas. I am going to share my screen and come along. Okay, can everybody see my screen?
Nope. I think you might need to select which screen.
All right. Hey.
There, it's coming.
Okay. Hey, there it is. Okay.
And so now we see it.
Okay, then I'm just going to jump into it. Thank you very much, everybody. My name is Vince Roux. I am one of the owners and the lead researchers at Off Planet Research, and we are a private research and development company in Everett, Washington, and we replicate environments on other planets for the purpose of developing and testing technology and processes that are bound for the moon, Mars, and other worlds. Our current primary focus is the moon. So I wanted to briefly review some aspects of how the lunar surface is different from the Earth's and the difficulty this poses for adapting technologies. And I realize some of this will be review for most of you, so I will go through it with purpose, but not too quickly. Let's see. There we go. The moon and similar bodies in space have no appreciable atmosphere to protect the surface or the people that are on it, as we all know. So one consequence of this is the processes of soil formation is primarily driven by impact. This produces regoliths that are very destructive to technology and dangerous to life. And just as an example, in the lower right-hand corner, you can see two images. One of them are grains of sand from an average Earth location, and right next to it are regolith grains, and you can see there's a dramatic difference because on Earth most of the soil and sand particles are produced through abrasion through either aeolian processes or through water or other types of polishing. So that is not present on the moon, and that creates a lot of differences, obviously. One thing to remember that I'm sure, once again, everybody is aware of, but it does bear mentioning that we are coming to the end of a more than 51-year desert of lack of human activity on the surface of the moon. And that creates an awful lot of challenges for us that we're going to have to make up for in our technology development. As we go through this discussion, we have to keep in mind, I already did that one. Okay, when we talk about developing communities on the moon, it can be helpful to identify stages in that development. And I actually use this an awful lot when I talk with clients. They say, hey, this is what we want to do. And so it's like, well, is it a first, a second generation? And not to try and cubbyhole what they're doing, but it does help set expectations for how soon it could be utilized on the moon and what the path moving forward is in developing the technology or adapting it as far as financing and the urgency and how fast you can move or need to move in that product development. So I usually divide these stages into four generations. The first generation being the one that we have now, which is primarily based on expeditionary type activities. So CLIPS missions, the Viper rover is going to be going soon. Artemis 2 is going to be launching sometime in the next year, supposedly, and getting the Lunar Gateway. And those are all missions that are intended to pave the way for human activity to return to the moon. We're looking at an increase in commercial launches and LEO activities, and the work is intended to progress to close lunar strategic technology gaps, as well as technology or strategic knowledge gaps, and develop lunar technologies. First generation technologies generally are going to need to be transportable by existing or rockets that will exist in the near future, as well as lunar landers in the same categories. So they all have to fit on there, and they all have to be able to function with the power supplies and space requirements, that sort of thing, for these types of missions. Second generation technologies are going to support the initial lunar communities, and they would include equipment and processes for prospecting, mining, and ISRU operations. It's very likely that these communities will also need to produce entirely made in space parts for satellites, spacecraft, and lunar base use. One of the areas of focus would likely be high mass components that would be difficult or expensive to launch from Earth. So this is where we start to get some payback for the investment of having an ongoing human presence on the moon, is, as other people have mentioned, producing components that we're going to use locally rather than transporting everything to the Earth. And the sooner we can prove that that part of the equation will work, the better it's going to be for everybody, and the faster we're going to progress in this effort. For those looking on the Earth for analogs of second generation type base facilities, basically container homes I've always thought are a really good analog, because it gives you an idea of the modularity. They're about the right size to be transported by a rocket and landed on the moon, and they plug in together. The nice thing about using these as an analog is when you talk to people that are developing technology and you're thinking, oh, it's going to be a second generation technology, you can say they need to fit in this kind of space, and they need to be able to function in here, and they need to be able to utilize what is going to be provided for infrastructure, for cleanliness and power and resources. So helping them envision this as an example is always, I find, helpful. These generations are the development window of greatest immediate need. That's because they're very near future, and in broader terms, there's existing financial commitments from governments and larger private organizations, and they fit within industry plans for the near future. The funding sources for these are also a little more reachable. They tend to be venture capital based or from personal investors, or they tend to be funded by grants such as SBIRs or NIAC if you're in the US. These sources these sources of funding usually want to have some sort of terrestrial based technology that is relatable. So, as we all say, what's the payback on the Earth? How is it going to benefit everybody? And usually these people want to see that not only as an additional way of selling what you're doing, but also as a way of helping to assure that there will be some return on investment if it's a non-grant funding source. The only exception to this would be a government contract for a specific item, where it doesn't, at that point, your client, the government, doesn't necessarily care so much about whether or not you can directly link it to a human use. It's for a specific mission purpose. And so that context usually is not included in the decision process. Third generation of this would generally be, I don't like this, but it is a good analogy, a company town, where it has expanded industrial capabilities such as mining, commodity production, and that sort of thing. It is very much oriented toward producing products and commodities. For electronics, it can produce high tolerance components for spacecraft and space stations, but it is still not something that, like if you go to Silicon Valley, where you have this full, complete capability of producing very high-end products, but it's on its way. A good example, like I said, when I'm talking to potential clients about what it's going to look like and what their technology could be in, I basically say, think of a cement plant. It's a very dirty, dusty environment, and they're producing commodities, but it is not something that you necessarily want to function in without a lot of protection. So basically, definitely function over aesthetics. It's not going to be the shiny, clean environment that we see in sci-fi movies. But at this stage, something remarkable should start to happen. There should be sufficient resources on the lunar surface for people to have some free time and a little more room to operate, and some power that can be that isn't entirely used for production. And at this point, I think you're going to start to see a very remarkable thing, which would be the first emergence of fully private industries or cottage industries, where people can have a little extra time and they can produce something and provide it to their fellow lunar residents on an exchange basis. And it's probably going to be something like what you see in this picture, something to relieve the monotony, something to make life more bearable and more human. But I think at this stage is where you're going to start to see that. And that's when I think human presence on the moon is going to become extremely interesting. And this is where, if we get to this point, it's like, yeah, we're there. We're going to keep going. So that prospect excites me. The fourth generation would be the full lunar cities, where they're very large scale mining and resource extraction, very large scale structures, very large scale agriculture, precision and high end industries can function, producing things like full integrated circuitry. And there's also would have high quality port and transport infrastructure. So once again, talking with clients, talking with people who are proposing or trying to develop technologies, understanding where their technology could fall in this progression of generations of lunar technology can be very helpful in trying to frame how they're going to proceed. Something that's very interesting, though, is that even in each one of these generations, there are multiple environments within the generation. So the lunar environment, the raw lunar environment on the surface is obviously the most challenging. It has all of the issues that we've all been talking about the presence of or exposure to lunar regolith and temperature and hazards such as radiation, vacuum, that sort of thing. The next environment that people need to consider for their technology is the transition areas, or the dirty work areas, such as airlocks or service areas for rovers, where it needs to be constantly cleaned. It could be exposed to transient vacuums as equipment is brought in and out. And this is also going to be one of your primary lines of defense, of keeping the lunar regolith contamination out of living areas and clean areas, such as the things that we see on the right, where you have shirt sleeve environments for human activities, everything from eating and getting a haircut to just generally living. And then also in these shirt sleeve environments, this is where you're going to start to be able to have things like 3D printing, and you can start working with more advanced processes that do require a clean environment. And so these are actually going to be present in various ways for each generation. It's just a question of what size of the, for instance, the clean type of environments, the shirt sleeve environments, what size are they? How much other resources are being provided to it, such as power, that sort of thing. And that also helps drive when technology can get to the moon and how it can be adapted. So what we wind up with is an iteration of technology where you get it to the moon and you set it up and you run a demonstration and show that it will work, or show what is needed to make it work. And then as you progress through these generations of technology, as well as how within each one of these generations, the environments become more available with more resources in each environment, then you can start to iterate the technology and begin to refine it to become more and more productive, building on itself to get to where we want to be with fully functioning cities and a higher quality of human life on the surface of the moon. So keeping all of that in consideration, what we wind up talking to people next is what it takes to adapt technology for lunar use. And a good example of this, something that everybody can relate to, is a standard electric motor that is present in, say, a table saw or a vacuum cleaner. something along those lines, because it has all the components that you have to pay attention to when you are trying to adapt existing human technology or new technology. But let's face it, all technology is based on what came previously. So there's always an element of adaptation. So going through a couple of points, the casing has to be a very low mass casing because you're either going to produce it on the moon and drive it around, which takes energy, or you're going to be transporting components to the moon. The second thing, you want dust tolerant connection hardware. So where the hardware hooks into where it hooks into the reduction gears to hook it up to the rest of the equipment. This is where you start running into issues of parts jamming together or parts not being able to be assembled because they are not designed to operate in the presence of regolith. So this is where you have to start worrying about regolith at a very early point in this adaptation. The extraneous components, so in this case we have a cooling fan. You may need to have something that protects something on the surface of the component, but you have to think about, just because it's something you would naturally put on Earth doesn't mean you're going to put it on something that's in space or on the moon. Cooling is always going to be, if you're out in a vacuum, it always has to be a radiative cooling. So you're going to be replacing cooling fans with radiators. And even if you're indoors, especially with equipment that could go outside it, you're going to have to always design it for the most demanding environment. So heat radiation is going to be a real problem and a real concern. All of the bearings have to be dust proof, or at least the seals on the bearings have to be dust proof. It'd be best if the bearings are dust tolerant, as if they could continue to function even if there was the lunar regolith in them. But when you're dealing with trying to seal out dust with a moving component, it gets really complicated. It is doable. We've done it before. We have done some work and developed some products that are very helpful in that environment, but that is where your primary intrusion of dust into the really delicate inner parts of these kinds of things is going to run into its first layer of protection. All of the fasteners would need to be dust tolerant. And when we say dust tolerant, what that means is they have to be able to function in the presence of regolith or dust. So you're going to need to have different types of threads on a very simple basis. Most threads that are common to use in an Earth environment will seize up almost immediately in the presence of any kind of regolith. That was one of the first things we learned when we got into this business. All of the joints will need to be dust sealed, because once dust gets inside something or gets into where you don't want it to be, then it's there, and it's very difficult to get rid of unless you totally disassemble and clean everything. So sealing out dust is a very important thing. All electrical connections will also have to be dust tolerant. So there's a different type of design for brushes and connectors that you would use to make sure that the dust doesn't separate your contact surfaces and prevent communication of electrical signals or just transmission of power. All of the coatings have to be space rated and provide thermal management in some way. You either want to absorb heat, or you want to radiate it away or reflect it. But finding coatings that will last a long time in space is very difficult, because most coatings have at least some form of polymer in it. Polymers don't last very long in space due to they basically evaporate away in the vacuum of space, and then if they're exposed to temperature extremes, that also degrades very quickly. So all the electronics also have to be radiation tolerant, and that's everything down to even just a simple resistor. It has to be radiation tolerant. So when we talk about radiation, we're talking about the whole spectrum of things that can interact with electronics in ways you wouldn't expect. And they also need to be dust sealed. Some of these things, the items in black, are general for space. Some of them are also specific to the moon. The blue ones are specific to the moon or Mars or wherever your dusty environment is. Overall, I mean, those are specific to something like an electric motor. Overall, magnetic and electronic fields, lunar regolith and Martian regolith, for that matter, tend to be very responsive to magnetic and electronic fields, and it will coat anything that has even the slightest field. And that can affect your thermal properties, and it can also affect, if it's an antenna, it can affect your transmission of or reception of radio waves. It adds weight to rovers. It adds weight to any kind of transport device. So you have to be very careful about that, and you have to understand that. Thermal extremes affecting fit and function. As things heat up or cool down, they tend to fit differently, so you have to pay attention to that. It has to be serviceable and repairable under lunar conditions. That's basically an astronaut wearing gloves in space. Can they actually get it to the equipment and service it, and at least get it back into a repair facility? And finally, all the seals and lubricants and coatings, as I said before, have to be space rated. So these are a lot of the things that you have to pay attention to when you're adapting technology to work on the moon. And when you look at a picture like this, where you have all kinds of stuff going on and you extrapolate that out, all of a sudden you realize what a big job this is. It's not something that will stop us, but you definitely have to pay attention. And a failure at any point in these type of operations can have a negative effect. So you really want to pay attention to this and test the heck out of it. I realize we're at 52, so I'm going to speed up a little bit. One of the problems, or not problems, one of the misconceptions we run into when we talk with people is there's an assumption that the regolith on the moon is, there's not a lot of difference between the different types of regolith in the different regions. That is actually not true. There's a lot of variation in lunar regolith depending on where you're at. And that includes everything from the maturity of the regolith to the presence of agglutinates to volatiles, frequency and size of rocks, anything larger than a millimeter. So this all has to be taken into account when you're doing your testing. So you need to test with a lot of different simulants in order to make sure it's going to work. And so you want to use different types of simulants. These are some of the examples of the different types of simulants that we produce to approximate different locations on the lunar surface. And we also can specialize simulants such as increased magnetic response for things like not coating electric motors, or for helping with benefaction processes. Agglutinates are something that can really affect the design and testing of components and methodologies for extraction and that sort of thing on the moon. Agglutinates are basically formed by micrometeorite impacts, and they do the same thing on the micro scale that they do on the macro scale. They excavate a crater, they melt some material, that material then bonds to other forms of regolith, and you wind up with this agglutinate. And they have very unique physical properties, and they are very destructive. I mentioned specialized things. Iron is something that is talked an awful lot about. It is very present in lunar regolith, but not so much on Earth. The origin of the iron can be either from the soil itself, or it can be from solar implantation. And its form and distribution on the surface of individual grains is very important for certain types of testing, like benefaction or dust control. And this is one example on the right of one of the types of simulants we make, where we have nano-sized iron particles that are physically bonded to the surface of these different regolith grains for doing this kind of research. Water, as everybody said, is very important, and this is really something that's very helpful when you're talking to people about water. Regolith in the equatorial and temperate regions on the moon, you tend to get about 1 water bottle full per ton of regolith. If you go to the polar regions, you can get an awful lot of water, about 15 gallons of water per ton of soil in certain parts of the polar regions. So this is why that's very important. And of course, water is very valuable. So where you're at is something that you want to pay attention to. I love this video. This is some of our simulated lunar icy regolith that you would find, the real thing in PSRs on the moon. And several other people have talked about this during the conference, about the fact that it's not just water, it has all these lovely chemicals in it. And dealing with them is something else that you want to consider when you're designing technology, because different types of materials are not compatible with some of these components, especially when they warm up and start to volatilize off. They can cause some real problems. Well, I got 5 minutes. I did it. Woohoo! I want to thank the Moon Society for inviting me to talk to you all today. And we've got about 5 minutes. If anybody has any questions, I would love to talk to you about them. So I will relinquish control.
Yep, thank you. And there are a couple of questions. Where did they go? James Sloan wonder, how large is your company?
We're a relatively small company. There aren't very many people. That is because we specialize in doing the research and development of products and advising other people. So it is myself, my business and research partner, Melissa. Lauren is someone who is also working with us full time. And then we have several other individuals that we call in for specific projects, but that's our core group. We have made some progress in some of our other business ventures relating to space, so we're looking to add some people, but I can't really talk too much about that right now.
Yeah, and Madison Feehan wonders, what is the accuracy of the IC regolith simulant? Accuracy, I guess, needs to be measured as well. And how does uniform particle size impact its realism to in situ regolith on the Moon?
The IC regolith, the great thing about that is we can tailor it. So we help test the nervous system that's going to be on the Viper rover, or at least the engineering version of it. And they came up with some very specific recipes for the ices they wanted to test their instruments with to make sure their instruments would work. And we were able to match that ice within a couple of percentage points. And there's various ways of doing that. You can monitor the gases that you're freezing into it, and then you can also sample it and thaw it out, extract out the gases, and see how much you got, so you can determine that. And the question about particle size distribution, what was that question again?
How does uniform particle size impact the realism of the IC regolith to in situ regolith on the Moon?
That is, particle size distribution is absolutely critical, especially when you're talking about mechanical properties. The regolith itself, manufacturing that simulant is a very controlled process. We are very careful to crush down the rocks and then sift them with several different particle size ranges, and then we mix them back together again, so we can control that very tightly. The ices, that is such a big question. We only have one solid data point, it would be the L-Cross mission. That indicated that the ice was intergranular in nature. That means that it's very fine particles of ice that are either frozen onto the regolith particles or independent pieces of ice in between the regolith particles. Once again, they tend to be very fine. That's why when you're doing this testing, vapor deposition is the way to go, because it's the only way of replicating that. And we have found that very small changes in the either the ice particles or the regolith particles makes a very big difference in the mechanical behavior of the simulant, but also in the chemical reactivity of it, because surface area relative to mass of the particles. It is very critical. The key thing is when you're doing research and development, you want to test with a range. So you want to establish what your expected perimeter is for any type of variable, including particle size. And you want to test your end members, and then you want to test a couple of points in between and make sure that what you're doing will work across the full spectrum. Gives you a much better chance of actually achieving your goal that way. And it's very critical.
Great. Philip Krum asks, what are some low-hanging fruit research areas that the Moon Society could participate in? Assuming we could make a dirty vacuum chamber and wanted to study regolith management, what could we do?
What's the low-hanging fruit of?
Dirty eyes.
Oh, well, Melissa, my research partner, recently said, I told her I was going to do this, so I'll throw her under the bus. I used the word low-hanging fruit, and she looked at me and said, no, it's the dangerous fruit. The icy regolith is the dangerous fruit, not the low-hanging fruit. And I think she's right. The low-hanging fruit, that's going to depend on a couple of things. It's going to depend on how fast you can develop the technology, and there's a lot of people working to develop technologies to work in this environment, and they're all doing their best. They're all remarkable people, and I think we're going to have to basically attack this problem with as many technologies as we can, as soon as we can, Some of them are not going to work for reasons that we could not have possibly imagined, and other ones will surprise us and work really well. But it's all learning. So I don't know what the exact low-hanging fruit is. I would take everything you got, everything we can throw at it as fast as we can and get it there, because the sooner we can start showing results, the more support we're going to get as a community to continue to do what we need to do. I hope I answered that question.
I think so. Yeah, I think that was a quite a good answer to a rather difficult question.
That is a difficult one.